Today we're going to look at sampling and the Nyquist criterion. We kind of hinted towards that in the last lecture, but we're going to look at it in detail today. And then we'll play around with a MATLAB script that will be available to you after the lecture to continue to experiment with. Are there any questions from the last lecture that we should clear up before we get started? Okay. I'm going to turn. Oh my. This was the good setting last time, and I've set it here, and the lights are not changing. There we go. That's too dark. I don't want to get rid of those house lights, but can you see the screen okay? All right. Okay. Okay. So sampling and the Nyquist criterion is basically the topic of today's lecture. And you know, we live in a entirely digital world essentially now, except for audiophiles who prefer to have, say, a turntable with a stylus and a you know, linear or an analog amplifier, which is harder and harder to find these days. But essentially what digital, you know, encoding does is it takes a signal that is a continuous function of, say, space or time. If it's space, it's just waves, you know, on the ocean or on in your image. If it's time, it can be music or somebody speaking. And so that analog signal, so let's just call it a voltage as a function of time, is converted to a sequence of numbers, right? And those numbers represent the amplitude and perhaps the phase of that signal as a function of space or time. And so now, instead of having this function that's defined everywhere continuously, we can ship or transmit that function as this set of numbers, right? Instead of the functional form itself. Sometimes that's more efficient. If this analog function has an actual analytical expression, and all you have to do is remember that formula, then that's very efficient. You can always generate that signal. However, in life, most of the time, that doesn't happen, right? There isn't an analytical function that especially in imaging, that we're dealing with. And so instead, we sample that analytical function and we store these values. And so it's a finite set of values, right? You know, in basically every electronic device you use now is exchanging information with other devices by passing sequences of numbers, yeah? Oh, on the Zoom, it's not centered? Oh.
Yeah, it's kind of 1/4 of the screen on the top left instead of a full screen. So,
oh, really? Here, let me stop sharing and I'll reshare. I'll see what happens.
Yeah. Okay.
Okay, thanks for shouting out. Sorry if I missed that. Okay, wait a sec here. That's all I want to do. I want to now share screen again. Share my whole desktop. How's that look?
Yeah, so we see your screen and now it looks bigger. Yeah,
it looks bigger. And if I go to that mode, is that okay?
Yeah, that's perfect. Thank you.
Oh, great. Okay. Thanks for correcting that. Okay, so that's you know, discrete or digital electronics / digital imaging, digital music. And so this is what we're interested in, which is a two-dimensional function, right, of brightness. And each brightness level in this two-dimensional function gives us a representation of the relative amounts of X-rays that have been absorbed by this object, right? So if it's bright in this area here, it absorbed more X-rays here than it did over here, which is dimmer. And both of these absorbed way more X-rays than, say, back here where you have very low value. Okay, so this is a picture. it's a CT scan of an axial plane or a slice through a human. This is their chest. Up here is air above their chest, their anterior wall, sort of the front of their chest. This is their sternum, a bone with bone marrow in it. That's the sternum. And then these are lungs as we move down through the chest. This is the top of that person's heart. When I say the top, I mean the part of the heart that's close to the head as opposed to the feet. And this slice of the person is only 0.625 millimeters thick, which is a very thin sample through that person, right? The representation of each one of these values is representing the X-ray attenuation in a slice through that person that's 0.625 millimeters. Just think about that for a second. Millimeters are a very small unit. It's half of that, right? So CT gives you extraordinarily high spatial resolution in both the slice direction and the in-plane direction. So it actually looks like a continuous function when we look at it this way. But if we zoom in, we can see that, you know, in some regions where you have ramps and structure like that, you can see the finite size of those estimates. They're little boxes that we've displayed the image such that the distance between each one of those boxes is the sampling rate in space. Right? Let's zoom in even farther. So we'll start. We're going to zoom in on this field of view right here, because this is really interesting, actually, what's in here. We'll zoom in once, zoom in twice. Okay. So now we're looking at that image, except we've put our face very close to the screen, and we can see that, okay, I now see those discrete estimates spaced in space. Right? Turns out this is a little part of this patient's coronary artery that's coming into this slice and then leaving the slice. And so the blood in here is going down into the heart through the coronary arteries. This is the patient's aorta coming out of the top of the heart. This coronary artery is connected to the aorta, but not in this plane, in this other plane. This little white dot here is in the wall of the coronary artery, and that's a little chunk of calcium, right? And that little chunk of calcium is indicative of the fact that that person has grown a coronary lesion at that spot. It probably flared up and it's healing, and it produces this little chunk of calcium. It's like a little rock of calcium. This is one of the best predictors of whether a person is going to have a heart attack in the next 10 years is how many of these little rocks do they have in the coronary artery. And you can do it trivially easily in a CT scanner. You just lie down, shoot them, and you look for these little rocks. Right? Yes? Absolutely, that's what these are. These are the image pixels. And they're square because the spacing in the Y direction and the X direction is the same in terms of our sampling. And you can think of these as little cubes, right? And except they're a little longer in one direction, the Z direction. They're 0.625 millimeters in the Z direction, and they're about, I think here, probably about 0.4 millimeters in X and Y. It actually doesn't make any sense to display an image when you're zoomed in this far, to display it such that you see these pixels, right? Unless you want to know how big the pixels are, because that is not what the object looks like, right? It isn't built of little blocks like that, like Lego, right? So it makes more sense to smooth that thing, get rid of those hard edges, and this is probably more like what's in there, right? And all we've done there is we've just interpolated between those discrete values to make a much smoother thing, and used many more pixels to make that picture, right? It doesn't change your fundamental resolution. All it changes is how many points you choose to display. Your point spread function is the same regardless of how many pixels you use. But you can resolve the actual point spread function, what it looks like, with many more pixels if you do this type of interpolation. Quantitatively, if we look across a row in this image, So we'll say we'll fix the y value to a constant, and now we'll just drive across different x values. And we can just read out the digital values of these pixels. And in CT, these are usually stored as integers. And those integers are anywhere from -1,000 to 5,000 or something like that. Historically, we'll see why that's true. And as we drive across this sampling here, you can see that there's a dip, this dark spot here, and then there's a peak, and that's this thing. That's that feature. That's what it looks like, you know, with these steps or individual pixels. When we look at the interpolated values, this is probably more like what's going on under there. And we can see the amplitude of the peak with respect to the background. Now, going back to our image noise discussion, if we look at the background of this picture, say this area right here, right? This is blood, and blood is a fairly uniform, homogeneous substance, right? It's been mixed with a contrast agent, so that can have different values of concentration as a function of position, but this looks like it's pretty well mixed. So the variability in the signal here, this bumpy terrain right there, is basically noise, right? We know that. A priori, we know that that blood signal should be about the mean of that bumpy thing. And many image processing and reconstruction techniques take advantage of that and say, look, if there's a space that's flat, all I have this bump that's at the noise level, we can shrink that down and make it look prettier. And some manufacturers do that. It becomes a little more challenging to do that when you have individual structures that are right close to the spatial resolution of the system. Is it a peak or is it noise, right? So that's the fundamental question. So that was an example from an actual clinical image of what we're going to discuss, which is sampling. And sampling just means I take my function, and here we have this function we'll call fxy. So this is the x direction, y direction. The brightness is a function of position, where the fxy value has high values here, right? Because there's something inside this person's head that is giving off a lot of MR signal right there. Lower values here because this is cerebral spinal fluid and it gives off a lower MR signal than the surrounding brain tissue, right? Which gives off this gray value. So this is our fxy. We use it as an example, as a backdrop to just say, what happens if we sample this picture at different rates? And when I say sampling rate, I mean, how often do I sample it per centimeter, right? So I take 4 samples per centimeter, 1,000 samples per centimeter, or, you know, half a sample per centimeter. That sampling rate can also be described as the sampling period, just like any other function. And the sampling period is this delta x, and that's the distance between adjacent samples, right? The sampling period. And this is delta y. If looks like I approximately double my sampling rate, or I reduce my sampling period by a factor of 2, I would sample these points on that function fxy. Both of these sampling rates are hopelessly low for trying to model or sample this function, right? There are many more details in this function that we're going to miss if we sample it at this rate, right? So part of our question today is like, how do you decide how many samples you need to adequately sample this function? It's obviously way more than we've got in either one of these examples. Well, let's say we reduce the sampling period by a factor of 500. Is that enough? Let's say 5,000. Is that enough? Right? So that's somewhere in that zone that's the interesting questions get asked. But just to set up the arithmetic for how this is used, and when you look at sampling as in linear systems, you need to write down a function. So we have our continuous function fxy, and we want to generate a 2D discrete signal. Discrete meaning I just have basically a sequence of numbers, and they're indexed by M and N, and that's going to represent my image fxy. Right? And we can do that quite easily just by plugging into fxy values of x and values of y that are essentially discrete steps in delta x and discrete steps in delta y. Okay, so for each m and each n, I just evaluate what x is and what y is, sample the function at that, and that becomes my discrete estimate of the function. Very simple. And these are called the sampling periods, right? Inverse of these sampling periods gets two names, and I'll probably use them interchangeably: the sampling frequency or the sampling rate. Right? So where does this come into play at the image acquisition time point in CT? It immediately comes into play because our camera, our X-ray camera that we're going to take the raw data with, has a discrete array of X-ray detectors. Much like your telephone or your mobile has a discrete array of detectors in its camera. And nowadays, usually that discrete array is 3K by 4K detectors. It's a lot of detectors, right? Like 12, that's why it's called a 12 megapixel camera. And it's got 3,000 by 4,000 pixels on the detector. You can buy the darn thing for $500. So you can't buy a CT scanner for $500. Anyway, the detectors on the CT scanner are basically the same. They have an array of detectors that when we shine the X-ray through the patient, we sample it on this array, right? So we get discrete estimates of the X-ray fluence across the integral of that square in that array. In early CT, when they used to do one slice at a time, they would have a single detector row element, and say there's 512 detectors across that element. And that single row would capture samples through the patient, right? In a parallel beam. In fact, in a parallel beam situation, if I have an X-ray emitter here and I blast X-rays this way, and I have a single detector here, I can just raster that single detector across while I'm taking my data. Right, so I really only need one detector. And at that point, you're just integrating X-rays over time, stopping, storing that number, integrating some more, stopping, storing that number. However, it's much faster if you have an X-ray source that gives you a fan beam of X-rays. So a set of X-rays that go from the source and go out just like a fan, right? And simultaneously, you can detect the project or the shadow cast by that source through your sample at whatever angle the respective detector element is at. Okay, so if my sample's sitting here, this X-ray goes through the sample and I, basically detect the shadow from that X-ray beam right here in this detector. So what corresponds to the sampling rate here? Let's just the separation, 1 over the separation of the detectors, right? If I have 100 detectors here, right, and they're separated by 1 centimeter each, right, I can up my sampling rate by making 1,000 detectors and making them 1 millimeter each, right? And so now my sampling rate has gone up by a factor of 10. And this is the way CT scanners were for probably 15, 20 years, right? They made a single arced row of detectors, usually about 1,000 detector elements, and a source, and then you would rotate that source around the patient and get different views on this detector element. Modern CT scanners, like in the last 5 years, everybody that's buying CT scanners, or maybe in the last 10, 15 years, have not just one row of detectors, they have a whole set of detectors stacked one on top of the other. So it's a 2D array. It's like if I had 64 of these, I've got 64 simultaneous CT scanners going, right, of the old school. So it really increases your, data rate in terms of, acquiring data in the Z or the slice direction. I get those slices almost simultaneously. So again, the sampling that's going on is the separation of these detectors in 2D. So now I have a delta Z, which is the slice direction, and delta theta. So why can't you just make more detectors? Just instead of making this, say 256 by 1000, why not make it 12 megapixels? Right. We'll think about that. So here's how the modern scanner is set up. You have an X-ray source up here. This is, remember, we looked at these in the first lecture. This is like an X-ray light bulb, and it has a little port right here, out of which the X-rays come. All the X-rays that go in sort of random directions this way from the source are filtered out. So I have a beam coming out of here. It's called a fan beam. We put a filter in front of here. Remember, we put a copper aluminum filter to get rid of the low energy X-rays. So now I have this nice geometrical fan beam of X-rays coming out. It has, it can cast a shadow for any object that's about 50 centimeters in diameter or smaller. If somebody's bigger than that, we're out of luck, right? Because some of them of their body will be out here, right? So we'll be missing in many views. Or if their arm is out here, there's a problem, right? It's missing in some views. And our detector element is this thing down here, okay? That whole thing's going to spin. When you take this cover and the skins off the detector itself, this is what it looks like. This is from a GE website. You can look at all of the movies associated with this thing. It's a really cool website. So they've, along this way is theta, or this is right left if the patient is lying in the scanner. This direction is head to toe direction, or the Z direction, it's usually called. So this is like a chunk out of the donut, right? A big 45-degree or slice out of the donut. And then the detector elements themselves plug in here as units. So they're replicants, and they just plug in. When you look inside one of these units here, right down here is the detector. You can see the little detector elements along there. This is an anti-scatter grid, which we'll talk about a bit, but there's the detector elements along there. So let's just pop the top of this off. There it is, popped off. And here are our detector elements along here. Okay. Now remember, we've taken out this thing out. So across this way, it's pretty narrow. We're looking, in the next view, we're going to look along this direction. Along this direction, this is Z. And then here's little chips, which each individual one has its own little array of detectors on it. When we pull one of those out, okay, this is sort of the fundamental unit. They make replicants of this thing and they plug them in together to make the full detector. It's 32 detector elements by 16 detector elements wide. This, just in this case, this is a GE detector. And then they're plugged in flush together to make a big detector field of view. Okay. And so this is discrete sampling right at the outset of CT, right? We're kind of stuck here, right? We can't on the system say, hey, let's dial up our detector resolution by a factor of 2 because I want to see some higher resolution stuff. Nope. This is your detector, right? So it's a big decision when a manufacturer decides, okay, we're going to make our detector elements the following size and we'll have the following number. Right? These have roughly stayed the same for 20 years or something in terms of the size of each individual detector on this array. They're usually about 1 by 1 millimeters. And the reason all of the manufacturers kind of iterated towards that is that, you know, if you make them a lot smaller, you might just run out of photons in some of those detectors. So if I cut them in half in both directions, so now I have 4 detectors for each one of these. Well, I need 4 times as many photons if I want the same number of photons in each detector element, because that's how, you know, and so the noise, the uncertainty in how many photons you've actually gathered in each detector element is proportional to the number of photons you measure, right? When you get down to low numbers, you get counting statistics errors, which give you wide variations in the values. And so I don't want to stay out of the region where you're only detecting a few photons in each detector. That's not a good situation to be in. So that's just called counting noise. And so they basically stayed this geometry for a long time, right? Just in terms of how much X-rays you can make with your X-ray tube and how many you want to put in a patient. One manufacturer, Canon, just said, to heck with it, we're going to make a high resolution detector, and they did just that. They cut these things into 2 by 2s. And so now they have a detector which actually is twice as big. It's like 2K by 512. Right? So that scanner actually makes higher resolution pictures. I've been in it, and the pictures are great, but you need more X-rays, right? And so for the Japanese market, it's probably okay, right? Because people are slim and they're small. If you go to Germany, where half of the people, you know, have a BMI of 30, you're going to have a lot of trouble getting all those photons through the person, right? So, you know, it's a balance. So in the particulars of this one, they just give it on the website. It's nothing, you know, it's not industrial espionage we're doing here. It's 256 detectors this way, 832 detectors this way, right? So that's our detector array for the scanner. Virtually all the images you'll see in this class come off of the scanner we have over in the Jacobs Hospital. And it's a Revolution CT, and this is its detector, right? And it's only, the model itself is only 6 years old or something like that, because it has this 256 detectors in the Z direction, which is a large number. Okay, any questions about sampling in CT? We sort of jumped out of sampling and into CT. We'll jump back to sampling now. Okay. So the process of sampling, let's say how we do this. We have a continuous function, f of x, and we're going to choose a sampling rate or a sampling period and just sample the values of that function at those. And now our function will be represented as this, which is essentially a set of numbers, right? That's, you can stick it in an array in MATLAB or whatever, and it's a set of numbers. And that's the function. So given a specific function, right? So whatever this function is, it's going to be dependent on what this thing is. How finely do we have to sample, right? If that function, let's just suppose the following. If that function was just a straight ramp, right? It was just a flat board, and it was dark on one side and it got brighter on the other side. It didn't change as a function of y. It just, as you went across an x, it went up as a straight ramp with a constant slope. Would we need a lot of points to sample that function? Nope, right? Because it basically, you can reconstruct that function if you have a priori knowledge that what you have is a ramp. You need very few points to reconstruct that function. The issue is we don't have a priori knowledge what our underlying function is most of the time. And so you need to sample fine enough to make a confident, you know, estimate of what's there. So it will depend on what the function f of x is. And if f of x has some very sharp features, which are things like if I'm going along at a nice flat, value, and I can sample and my value isn't changing. Well, I don't seem to need to sample very much. But then it discretely just, boom, there's a wall, right? And then it goes to another value. I need to know where that wall is, right? And so I need to sample at a high frequency to figure out where that is, where that feature is. Also, if there's a spike and you want to know where is the spike, then you're going to have to sample finally to make sure you intersect with that spike, or else it'll just get lost. And so what are the consequences if we don't sample finely enough for our function? And the fundamental sort of question to answer is, given the samples you've got in hand, can you use those samples to reconstruct an absolute error-free version of your original function? I've got original continuous function. I now sample it at a specific rate, and I have those numbers. I don't know what the function is. If I sample enough, is there a way to take those finite samples and reproduce my continuous function absolutely correctly? Right? The answer is yes. You can do that, provided there are properties of that function, f of x, which are in place. It usually means there aren't super sharp edges and there aren't super sharp points, right? If they have sort of more gently flowing features, when you have discrete samples, you can usually reconstruct that function adequately if you sample well enough. So let's take a look at an example of sampling in the time domain. This will have applications in MR specifically, because in magnetic resonance, what you do is you put the patient in a magnet and you bathe the patient briefly, say for a millisecond, in very high amplitude radio frequency energy. It's like an RF antenna, right? It's like they're standing in front of a big RF antenna at the top of the antenna tower. It's like, woof, I get all of these watts of RF. And then you shut that off and you turn on your receiver antenna and you listen. And it turns out RF energy comes out of the patient. It's like an echo. And you hear that, or you can measure that as a voltage in your antenna. So in MR, the fundamental signal you are receiving when you're making an image is time domain signal. It's radio frequency energy, right, in an antenna. And so that's a voltage as a function of time, right? Usually doesn't look like this, but this is just an example, okay? So here we have a voltage as a function of time, sampled at some sampling rate fs. Well, I don't know what it is. Looks like it's probably around 10 kilohertz, something like that. Okay, so it's sampled 10,000 times a second. And this is what the function looks like when you have that many samples, 10,000 a second, and you plot them. When you take the discrete Fourier transform of this and look at the power spectrum, which means what are the relative amplitudes of the sine and cosine waves that go into making this thing, the power spectrum in this case looks like this. A couple of things to note. This is time, okay? So this is 150 milliseconds to here, right? This is frequency in hertz. So this is 10 kilohertz or 10,000 cycles per second, okay? The amplitude of the sine wave, say at 2 kilohertz, is given by this value right here, right? That amplitude of the sine wave that's in here, creating this signal. Note that this is usually plotted on a log scale, this power. So these values here are close to 1, and these values down here are close to 1/1,000,000th of that. So there's a large dynamic range of values here. Now let's do the following. We'll take this signal and we'll move along, and every 8 points of our original sample, we'll only take one of them, and then we'll throw out 7. We'll take 1 point and throw out 7, then take 1 point and throw out 7. So now we've reduced our sampling by a factor of 8-fold. Okay, so we just have 1 point where we had 1 for every 8 before. This is what it looks like when you plot it. Okay, we'll do some of this in MATLAB, but and then when you take the Fourier transform, this is what you get. And that looks remarkably different, right? The reason it looks remarkably different is, as you can see, this function basically has unique values right up to about here, right? And then you just reflect those values, these values here, around this point and create this segment, right? So that whole thing is just a symmetric function around this point, which is just under 2,000 cycles per second. And then this whole thing repeats, right? It just repeats over and over and over again. Okay. And this is basically called aliasing, right? This is where the higher frequencies fold back into the values obtained at the lower frequencies. And then that whole thing just repeats at a specific interval that is governed by whatever my sampling period is. Okay. When my sampling period is very small, the interval of repeat is large. Here it's out past this 10K point. Here it's quite small, right? We can see that this thing is cycling at every 2K or something. So that's the consequence of downsampling or not sampling fast enough. Maybe this is sampling fast enough if all you care about are things below this frequency, but they're going to be corrupted by, you know, additional stuff at higher frequencies, right? So how does this work? If you have a sine wave like this, and this can be time or space, right? And we pick our sampling period such that when I put the sample points on the sine wave, they have this kind of separation. So in this case, one would say, well, we're sampled pretty well for this sine wave because we have many points. And when I connect those points, I basically see a sine wave. And I basically see it at that frequency. Right? If instead I drop every, I don't know, 20th point or every 16th point or something like that, and just use these points, now I can't really see that this is the underlying frequency. That signal at that higher frequency gets wrapped back into this estimate of this lower frequency. Right, so this is a sort of a visual demonstration of what aliasing is, and that is if you're not sampled with high enough rate to sample a specific frequency, that frequency, if it's in your signal, will give you amplitude at a lower frequency. Oh, this is a really neat demo. This is called the wagon wheel effect. I think I have it up. Wait a minute. Let me go back here. Try and, oops. I don't know if this is going to work, but we'll try. Oh, let's do a new tab. Oh, choice. Okay. All right, cool. Can you guys see this online?
Yes.
Terrific. So here's a disk, right? and it has a spatially repeating pattern on the face of the disk in theta as you go around. So everybody's lined up here, and you can see the frequency, of lines as a function of theta basically increases as we go out here. Okay. We're going to spin this disk and film it with a digital camera. Okay, and we'll see what it looks like. Well, now, what the heck is going on here? So as you can see, each frequency comes to a stop and then goes the opposite way, right? This is called the wagon wheel effect, and it is a absolute demonstration of aliasing. And so, as you can see, there's a frequency at which the pixels in the camera are flashing, and it is pushing basically this pattern in one direction or the other, depending on the speed of the wheel, right? Because the flashing in my camera at each pixel for that part of the field of view, is changing its frequency. The camera itself has a sampling frequency, right? So you know how on your iPhone now you have what's it called, slow motion. That'll up the sampling frequency by, I think it's a factor of 10 or something. And then in the normal sampling, it's, 20 frames a second, 30 frames a second, something like that. And so those are finite samples, or at a specific frequency. You can see this effect with your own eyes, actually. You have seen this in your life. If this is new to you, you have actually seen this sometime in your life, okay? And that's like if you're sitting in your car and a truck goes by, and it happens that the truck's wheel is turning at just the right frequency, corresponding to the frequency of your eye sampling things, then it'll look like the truck wheel is either stationary or slowly turning backwards, or slowly turning forwards, right? It doesn't look just like a blur. And it's called the wagon wheel effect because in Hollywood, in early Westerns, when they had a camera that was firing off at 20 frames a second or whatever, and they were doing a big chase scene and someone was in a wagon, people got fired because they came back with film and the darn wheels were going backwards. It's like, how could that happen? So basically it's mapping frequencies to places that they're not because of this interference of the sampling with the function itself. Okay, let's go back to, because I want to be it soon. Okay, so, okay. Are you guys back? Can you see the slides okay?
Yes.
Okay, terrific. This is an example from the textbook of aliasing, and it's a very subtle example in the sense that, I'm not sure you can see it on the screen, but you'll be able to see it in your PDF file, where if you have a chest x-ray, in the early days of digital imaging, they had a lot of analog films that they had in the radiology department, and they would feed the film through a digitizer in order to keep a digital copy of that image. And those digitizers back in the early days weren't that great, and they didn't have a super high sampling rate. And so the image you got out had artifacts in it. You can see the difference between the fine structure of the spine here and that in this digitized picture. And this was aliasing of high frequencies back into low frequencies. And the way you can get rid of it is if you understand what is the highest frequency your digitizer can sample, right? And you usually know that. Then you filter that out of your picture first, and then sample that thing. And then you'll get a high fidelity copy of a filtered image, right? Because it only has the lower frequencies. It doesn't have these high frequencies that get aliased back. Here's an example of testing cameras. This is probably from some geeky camera book or something I had that, there's two models of camera here, the D60 and the SD9. And you're taking a picture of just a coat hanging on a chair. Okay, so it's pretty innocent. And so if we look at this part of the fabric actually has a periodic pattern in it because it's a weave, right? It's made of something. When you look at it up close, it has some periodic pattern. Here, this camera is able either to filter that out or sample it well. Here, what happens is that high frequency aliases back as this wave-like structure in the picture, right? And so that's a lower frequency. This is like quite low in terms of cycles per centimeter compared to the frequency of the pattern in the weave, right? It was a much higher frequency. But in your picture, it looks like this, right? And that's sometimes called a moire pattern, and it's aliasing of these high frequencies. Okay, so we'll get there as to how this happens and how you can avoid it. To do that, we're going to use a few mathematical things, and so we're going to review those. We've done some of these already. But if we're talking about sampling, the most useful thing analytically is the comb function, right? And it is a set of delta functions. So remember the function delta x, just with no n in here. It basically, when you integrated the product of delta x times any function f of x, it brought out f of 0. If you offset, delta x by, or x by, or the delta function by some value delta x, it will sift out the function at that value. So a comb function is just a sum of delta functions. So you just write them out as this is a whole pile of them. Sum of delta functions with an offset such that it's an integer offset such that you get a delta function at each integer value. Okay. And this is very useful, obviously, because it looks like a function that you would use to sample something, right? You would integrate your function across this thing, and you would just get the values of the function at those points, right? Because that's what the delta function does. The impulse train is another term for this, or we'll just call it the comb function. Any other questions on that? So the comb function, as described in the book, you can do it in 2 dimensions just as easily, right? Where you have a 2-dimensional delta function with m and n as your offsets. And so now I have the transverse or the plane covered in spikes. And we saw that in the lecture last time. Oops, sorry. If you want to scale the delta function such that you're not just on integers, but now we can tune it so that we're going to have a sampling frequency that's tunable by changing our sampling period delta x and delta y. Okay. We can add that in by putting those here and here. Instead of having those values as 1, they can now be something other than 1, right? And we'll get a comb function that has separations, delta x, delta y instead of just 1, okay? And normally a normalization coefficient comes out here, right? Because if we make the sampling really, really close together, we multiply the output by this scale factor to keep everything normalized. That's in the textbook. You can look at that. This is the comb function in 1D that is scaled. So it's exactly what it did on the last page, only in 1D. Okay. So here's let's go back to, we just drew blue boxes on this before, but now we have a mathematical way of sampling this thing. We can say, here's our continuous function f of x, it's our image, say, and we're going to sample it at some period that we choose, delta x, and this is the function we will multiply it by. to do that sampling. And when I mean multiply, that's exactly what I mean. You just take f of x, and the comb function is a function of x, and just point by point on x, multiply those two functions, okay? And what it gives you now is a set of discrete values above the plane, or above, you know, like 0, where you have the values of f of x. Now, this function, f sub s of x, and when you read the textbook, it's worth keeping this in mind. This function is not a set of discrete numbers. Okay, that sounds confusing. This function is a continuous function that has zeros here, right? Zeros here, and the value of f of x here. So it's defined everywhere on, you know, the domain of the x values. Okay, it just happens to have zeros down here. So when you're starting to use it, you know, in integration and calculus and everything like that, it is a function of x. It's not just a set of numbers, right? We'll see how you get that set of numbers. So this is the continuous function f sub s, or sampled version of f of x, which is f of x times the comb function, right? And then you can write it out as follows. We know what the delta function will do. It will sift out these values of f at, you know, integer units of our sampling period delta x. So that's what the continuous function, the sampled version, looks like. It's right here, right? These are the actual numbers, right? This is a list of numbers, right? Okay. That seems like a weird point right now, but it's worth remembering. Okay. I don't know why we put sifting here. Oh, that was just to show that you could just put n delta x in here. It's using the sifting property of the delta function. Okay, so that's the sampling function. We've got a set of discrete points, and we have a continuous function in space. Exactly the same thing can happen in 2 dimensions. And when we're imaging in 2 dimensions, this is how it's going to go down, so that we get a set of discrete values as a function of m and n as a representation of the image, and then this is the continuous sample version. Okay, so what is the Fourier transform of a comb function? Well, that's interesting, isn't it? So what was the Fourier transform of a delta function? Anybody remember that? I think, oh, this reminds me. You should have in your head a little Pictionary, okay? And the Pictionary should have a little function, right? A little picture of a function on one side and a picture of its Fourier transform on the other side. And in your Pictionary of functions, you should have the delta function. You should have a Gaussian. You should have a rect function and a sine wave and a cosine. That's the little thing you carry in your pocket in the Pictionary of your functions. I don't know, is there another one, Tom, that's really useful to carry in there? Maybe a ramp? I don't know. Yeah. Okay, so using those, yeah? Oh, sure, yeah. So a delta function, know the Fourier transform of a delta function. Know the Fourier transform of a Gaussian blob. Right? Know the Fourier transform of a top hat function or rect function, R-E-C-T function. Right? Know the Fourier transform of sine and cosine. And now we're going to learn one more, which is the Fourier transform of a comb function. Okay, this one's important too. Okay, so here's our comb function. The Fourier transform of this guy. How is this working here? Sorry. Yeah. I don't know where I'm missing something here. Anyway, looks like we're just stating the Fourier transform of a comb function is a comb function. Okay. And we're not deriving it here. That it may be derived in the book, how that works out. But if you recall, the Fourier transform of a delta function is a constant. The Fourier transform of a comb function is another comb function in the Fourier space. And when we put in the scaling factors for here through this, the relationships that you know for the Fourier transform in terms of scaling, the Fourier transform of this scaled comb function turns out to be this set of scaled comb functions. And the important thing to note is that the spacing between the combs in the Fourier space is 1 over delta x, right? Whereas in space it was delta x. So here, if I have this comb function and I take its Fourier transform, I get another complementary comb function where the spacing between the samples goes to 1 over delta x, where this was delta x. And oh, here we go. So this is why we needed to sort of acknowledge the difference between the set of discrete values of a function and what the comb or what the sampled version of a function is. Okay, so here, if we have the sampled version of gx, and so what does that mean? That means we have zeros everywhere except at the sample points where we now have values of gx at those sample points. Okay. We can take the Fourier transform of that continuous function, and what does it? We break up the definition of gx into the product of, or g sub sx into the product of gx and the comb function. We then use the convolution theorem, right, which is really important. That's why the convolution theorem was so important, right? To express the Fourier transform of this product as the product of the Fourier transform of g convolved with the Fourier transform of the comb function. And that the reason we can do that is we know, the Fourier transform of gx is this guy. So when we convolve the Fourier transform of gkx with the Fourier transform of the comb function, we just plug in what that is right here, and we get this expression. And it sifts out these values, right? And we get essentially the sum of the Fourier transform of g as a function of kx, and then we get replicants of that every 1 over x, right? So this goes from n from minus infinity to infinity, and so we have basically the Fourier transform as a function of gx, and then the replicants as we move out in kx. And the way that looks is the following. We have essentially our Fourier transform, which is gx here, of just the function g itself. when we look at the Fourier transform of the sampled version of Gx, we get the Fourier transform of G plus these replicants every 1 over delta x. Right? And all is well and good in terms of representing what the Fourier coefficients of this function is gkx, if our delta x, or our sampling of the original function, is chosen such that the separation here is far enough apart that the power or the amplitude of the sinusoids, it decreases down so they don't overlap, right, between these replicants. If we undersample, that means this value here, delta x, is too big, then this distance in Fourier space becomes smaller, and these replicants get closer and closer together, and these values start overlapping. So what it says is we can actually, if we know ahead of time what the Fourier transform is over our continuous function, that is, we know the bandwidth of our function. We know what are the spatial frequencies required to make this function. If it is limited, if it rolls off and we don't need an infinite number of frequencies, if it rolls off at some point u, at some point minus u, then we have the ability to sample that function such that we can make an absolute copy of the original function just from the samples. And to look at that in Fourier space, what that means is it gives us a criteria for the sampling rate, right? And it just means that the sampling rate has to be larger than 2u. So if this is u here at the cutoff, sorry, u here, I need a sampling rate of 2u to make sure that the finite bandwidth of this function is represented. Unmute. Okay. Can you guys hear me again?
Yes.
Okay, great. Okay. When this condition, this little formula here, which is trivial, is called the Nyquist condition. That means given a bandwidth of a signal, we have to sample at a specific rate in order to adequately sample that function, such that we basically can reconstruct it, or we sample all of the spatial frequencies that are in the function. Yeah.
So does U represent the spatial domain Fourier space? Or?
U represents a position of cycles per centimeter in Fourier space. Okay, so it is a value of kx in Fourier space, and so it's a limiting value. It says any frequency higher than this, any wave number higher than this, we don't need that to make fx, right? That picture, because it's decayed away, or it's just not in there. And it's related now to delta x, which is the sampling period in space, right? Such that when you set the sampling period, you need to keep in mind that it must be small enough to make the sampling rate higher than twice this, 2u, right?
Can you please share your screen? Sorry.
Oh, thanks. We seem to go through some strange transition. Okay. Is that good?
Yes.
Okay. Sorry about that. I'm not really sure how it all transpired. I probably hit the wrong button. Okay. I'll go back. Yeah. in the book, they go through this argument as well, and it's true in 2 dimensions as well. What is true for f of x, in terms of y, it's exactly the same thing, right? So in that case, you will get replicants of the Fourier transform after sampling, where the distance between the replicants is, 1 over 2y in this direction, 1 over 2 delta x in this direction. So recall, this only happens when you turn your function into the function that is sampled with that cone, right? I'm not talking, if you take the Fourier transform of your original continuous function, you will just get the full Fourier transform. Now what we're saying is, well, what happens if I take the Fourier transform of the continuous function that has zeros, but then a value, zeros, and then a value, zeros, then a value, zeros, then a value. That's a different function, but it corresponds to f of x. When you take the Fourier transform of that thing, you don't just get the Fourier transform of the underlying function, you get multiple copies of the Fourier transform of the underlying function, and their distance between those copies is dependent on how far apart those samples are, right? So if the samples are really close together, the copies get farther and farther apart in Fourier space. Okay, so this is that same thing, just to keep going back to that same example where our delta x here is close enough together such that you can imagine you can reconstruct this function quite nicely. When the delta x is this far apart, this frequency is pretty well lost, and the overlap, and what's happening is if you look in the Fourier space, you're going to overlap considerably with this spatial frequency and this spatial frequency. Okay? We can look at a pictorial example of this kind of sampling. And here's our original signal in the top left, and we'll say kx in the frequency domain is 1 cycle per centimeter. Okay, and I'm going to plot that function here between -5 and 5 centimeters in the plane. Okay, and so I have a sine wave. It's not a function of y. It's just moving along through its cycles as I go along in x. Okay. The way this picture was made is the function was sampled 10 times per centimeter. So our delta x was 0.1. Okay. Kx, remember, of this function is 1. Right? And delta x is 0.1. That's what it looks like. Right? Same function, and now let's make delta x 0.2. We'll drop every other point. Right? When I just make a picture of that function, this is what it looks like. Right? And it still looks like a pretty good sine wave, right? I have a peak, a trough, a peak, a trough, and the distance between the peaks and trough is the correct distance. So I can still tell you that's a sine wave with a frequency of 1. Right? Delta x equals 0.3. Things are starting to break up a little bit, right? In terms of, so all we're doing, remember, is we're sampling this function at a lower rate and making a picture of those values. Delta x is 0.4. We start getting a function that looks fairly interesting, right? It no longer looks like a sine wave. Delta x is 0.5. We get this function. And we still can tell you this is a function that has kx, or the frequency of 1 cycle per centimeter, because I have a peak and a trough, and a peak and a trough, and a peak and a trough. It just so happens that it's 1 point up, 1 point down, 1 point up, 1 point down, right? So that's the only detail we get at this point, is what we know we're up and down, up and down, up and down. So, I can tell you that this thing has power at kx1. When I go past that, yes.
Probably mistake it for a spike train.
So the question is, would you mistake it for a spike train? You could indeed mistake it for a spike train, right? You don't really know what the details are under here. Like, you know that we know it's a sine wave under here, but here we have no way of knowing because all we have sampled is the peak of the sine wave and the valley. And so it could equally well be a square function, right? With that frequency. So there is this is where you're right at the limit of detecting that frequency. When we go to delta x of 0.6, you get this function, which looks quite different, right? We're starting to alias down into a pattern that looks like a lower frequency. 0.7, again, we get this much more slowly varying function, right? 0.8, here we have something that looks like a totally different frequency. So it's aliased back into a lower frequency. And 0.9, we get something that looks like it's just going through one primary cycle. And all that is it's just we're sampling at such a low rate, right, that we're hitting the sine wave at just the right spots to create this function. Right? So that's a visual demonstration of how undersampling leads to an estimating power in lower frequencies. Right? So here you go. This corresponds to 2 samples per spatial period when our delta x is 0.5. And it turns out to be, we need 1 over delta x to be greater than 2, right? Or delta x to be less than 1 over 2u or 0.5 millimeters. So that's the Nyquist frequency here. So here, we're sampling at a specific rate. These are delta x and delta y, or in fact, they're like sort of like delta x and delta z, because this is the z direction. But anyway, let's call this the xy plane. And can we avoid aliasing from this detector? And one way of doing that is there a way to filter your signal before it hits the detector such that those high frequency edges aren't in there, right? That is usually not done in CT. You usually just let the projection hit the detector and you deal with it later. Okay? And so if I have a tiny little dot, right, and it projects onto this screen such that that dot can be inside one detector only, and then as you move the dot around, it now gets shared between 2 detectors, and then it moves into the next detector and such like that. That will produce artifacts on a CT picture, right? Normally, you take that signal and you can do some smoothing on it to try and get rid of those artifacts. Okay, filtering can be done with functions that, remember, if we think of this, I mean, this is kind of backwards. These are Fourier pairs, but if we filtered a signal with this kernel, i.e. we convolved any signal with this function, when we look in the Fourier domain, it would be like multiplying by this function. And so we would get rid of high spatial frequencies, right? So all the frequencies out here would be gone. I am flipping this around because we know this is a Fourier pair, right? The rectangle goes to sync. I take the Fourier transform to sync, I get a rectangle, right? So there's sort of an equivalent here. Okay, so it looks like we've only got 4 minutes left. But what I want to do quickly, that took a lot longer than I thought it was going to take. I must have meandered. Okay. So I posted up a little chunk of MATLAB, and I'll just give you a quick demo so you know how to use it easily. Okay, so you can read through it, and this is just creating things in or functions in MATLAB to look at the discrete Fourier transform and how it falls out practically. So we have 512 points. We're going to look at a rectangle. So the way I do these usually is you put a double percent sign there, and then when anything's highlighted like this in your MATLAB window, you can just command return. I don't know what you're doing on a Windows computer, sorry. Command return, and it'll just run that. And so we can see what's happening there. And so what we've done is we've created a rectangle, right? It's, I don't know how many points, we'll take a look, but it's some points thick, and it's at the origin, and then there's these zeros, and we just take the discrete Fourier transform using what's on board in MATLAB. And this is a function, the real part of that function looks like this, right? So that's the sync function, right? And here's the real part of the function, the imaginary part of the function, and this is the magnitude of the function, right? So you can just take a look at this and say, okay, what would happen if I change the width of the rectangle to 4 points? So now I got 1,000 points here. No, 512 points. Let's make the width of the rectangle 4 points. What does the Fourier transform look like? Just run it again, right? Bump, bump, bump. So now it's a really narrow rectangle here. I look at the Fourier transform and I have this. It's a sync function, but it has the zero crossing of those waves is much wider, right? And notice also it's reflected about this center point. So what's with that? I mean, this is, why is the sync function not in the middle with a peak? Well, it kind of is, in the sense that this is zero frequency here going to higher frequencies. And then it reflects about this point and goes back to zero. So these are actually, you could consider the negative frequency, right? And the next little simulation in here, this is just that's the phase, and the amplitude of that